So far in this chapter, we've been trying to attach benzene to other groups. Benzene is the most common aromatic molecule, and it shows up in a lot of medications, hormones, and neurotransmitters. So, attaching it to other things to build those medications is really important. We saw that benzene has pi bonds in it, and in the different reactions in this chapter, we've been using those pi bonds as nucleophiles, and they've attacked different electrophiles. We had to create electrophiles with full positive charges in the different reactions at the beginning of this chapter. Those are the electrophiles that the benzene ring attacks. And when they attack, they replace a hydrogen that was on the benzene ring. So a hydrogen that was there gets removed by a base, and it's essentially just replaced by these different electrophiles. So those reaction types are called electrophilic aromatic substitutions. They're electrophilic because we combined electrophiles with benzene to make the reaction happen. They're aromatic because they depend on benzene. They're unique reactions that are required when you try to put something on an aromatic ring. And they're substitution reactions because they're replacing the hydrogen. So the hydrogen that was originally on benzene is being replaced by, for example, bromine or chlorine or whatever the specific electrophile is. Nonetheless, if you think about substitution reactions that you know so far, for example, SN2 and SN1 reactions, those reactions don't depend on electrophiles. Those reactions depend on nucleophiles. That's what the N in SN2 and SN1 means. It means you have to combine a nucleophile to make the reaction happen. Most reactions involving substitution are nucleophilic. In other words, you would normally see something like a benzene ring or some other ring, and it would have a leaving group on it like a halogen, some big atom that can act as a leaving group, and a nucleophile, like a classic nucleophile would be hydroxide, with its 3 lone pairs and full negative charge, would come in and attack the carbon that has the leaving group on it and kick the leaving group off. And you'd have nucleophilic attack that adds the new thing and loss of a leaving group that subtracts the old thing. And so you replace one thing with another, you do a substitution. And if you didn't have an aromatic ring, that would be the whole mechanism. But because we have these aromatic rings, it changes this reaction. So these next two mechanisms that we're going to talk about are mechanisms where instead of combining benzene with an electrophile, we're going to put benzene into a beaker with a nucleophile. And we're still going to force the nucleophilic attack to happen, and we're going to force the loss of a leaving group to happen. But because we have benzene rather than another molecule, because we have this aromatic ring, the reaction works in a slightly different way. If you think about it, if you look at this, in order for this reaction to happen, the OH has to get close to the carbon that has the leaving group on it. But because the leaving group is on a benzene ring, you have a lot of electrons there. You have 2, 4, 6 pi electrons. That's a lot of electrons in that ring. So as this negatively charged nucleophile, and remember nucleophiles are defined by having a lot of electrons themselves, and in this case they have a full negative charge, so this negatively charged nucleophile with a lot of electrons gets close to another place that has a lot of electrons, and like charges repel, so their negative charges would repel each other, and normally this would prevent this reaction from happening. The nucleophile would try to attack, it would feel the negative charge in the ring, and it would get pushed away, repelled by that negative charge. So to make this reaction happen, you have to do something a little violent, and that is you have to add heat. And that's going to be the case for the last two mechanisms in this chapter, nucleophilic aromatic substitution and elimination addition. So in both of those, you have to add heat. They differ in how much heat you have to add. In the first mechanism, we're going to see you only have to add around 70 degrees Celsius. In the second mechanism, you have to add above 300 degrees. So let's just say 350 degrees Celsius. So that's a big difference in heat. So why the difference? It has to do with a requirement. In the nucleophilic aromatic substitution mechanism we're going to draw out in a second, the reason why the reaction can work with less heat, and when you think of heat, you should think of how violently this nucleophile is getting pushed around. So when it smacks into the molecule, how much energy it has, how much it can resist the repulsion from the electrons in the ring. The reason this will work at lower temperatures is because when you do this first mechanism, you have to, in order for this to work, you have to have a nitro group para to the leaving group, so 1,4 to the leaving group. The nitro group is often abbreviated, just written as an NO2, but I want to draw it out here. We're going to have to draw it out when we draw the mechanism for this. The oxygen has a full negative charge, one of them, and the nitrogen has a full positive charge in this. So overall, the nitro group has a 0 net charge, but those two atoms have charges in them. The reason why the nitro group allows you to do this reaction at a lower temperature is because the nitro group pulls electrons out of the ring. It pulls them out of the ring. They go toward the nitro group. That's for two reasons. The first reason is that you have a lot of electronegative elements. The oxygens and nitrogens use their electronegativity to pull electrons out of the ring. The other reason is because of resonance. You have a pi bond between this oxygen and this nitrogen, and this lone pair could exist as a pi bond too. Those pi bonds are parallel and adjacent to the pi bonds in the ring, and so when those p orbitals merge, they can spill out into the nitro group, and that helps those electrons to spread out more, and means there's less electrons in the ring at any given time. So both because of the electronegativity of these the nitrogen and the oxygens, their induction, and the resonance that they have with the ring, they reduce the amount of electrons in the ring. The electrons get pulled toward the nitro group, and now this nucleophile just needs a little push. It's not being repelled as much because there are fewer electrons in the ring. So it just needs a little push, and it can attack that carbon there that has the leaving group on it. So let me show you how this would work in the example that's given in the homework for this, the nucleophilic aromatic substitution question in the homework. And we're going to be focusing on this scenario where you have 70 degrees Celsius and a nitro group para to a leaving group on your benzene ring. And the two steps we're going to do are nucleophilic attack and loss of a leaving group. Those are the only two curved arrow patterns that will happen in this mechanism. You'll just see that in the middle we get this odd, and you can see this in this mechanism abbreviation, we get this resonance stabilized intermediate. That looks a little complicated, but essentially we just have nucleophilic attack in the beginning and loss of a leaving group at the end. It's a classic sort of SN2 type reaction, except for the scenario where the electrons in this aromatic ring are repelling the nucleophile. So let's say you had a molecule like this here. We can draw our nucleophile, which is the OH, right? Sodium is a metal, so it has very low electronegativity. So it gives its electrons away to whatever it's bonded to. That's the oxygen, which has really high electronegativity. So this is an ionic compound, a metal and a nonmetal. Sodium is enormous. As atoms get smaller as their electronegativity gets bigger, and sodium is way at the left. So it has very low electronegativity. So its electrons really spread out, and that means it can really dilute this positive charge. And because of that, sodium is really, really stable. So it basically disappears into the solvent, and it doesn't interfere with this reaction at all. Let me make this black here so we can see the difference between our nucleophiles and the atoms. And so in the very first step, you'll take your molecule, and just like in any substitution reaction, the nucleophile attacks the carbon that has the leaving group on it. So that first step is going to be nucleophilic attack. And our leaving group is the halogen here. Just like sodium, bromine is really big. A bromine is about the size of a propane molecule. It's 3 carbons and 8 hydrogens. That one bromine atom is about that big. So the bromine will eventually be able to take these electrons and come off the molecule and spread them out over a huge space, dilute them, stabilizing itself. So bromine is our leaving group. And our nucleophile, in our first step, we'll do nucleophilic attack. It will attack the carbon that has that leaving group on it. So that's our curved arrow pattern, nucleophilic attack. Remember, in terms of storytelling, nucleophilic attack adds. It adds a molecule onto another molecule. Now, the electrons here, the carbon here, already has 4 bonds. So if it's going to form a new bond, one of the bonds it has to break. And that's going to be the pi bond. So this pi bond here is going to break, and the electrons will go onto the atom next door to the leaving group. Okay. So let me draw what that might look like for you. Make sure you draw out the nitro group. These 2 pi bonds have stayed the same. We still have this bromine here that hasn't left yet. We have a lone pair here now with a full negative charge. And we have our OH added onto this molecule. So our nucleophile has added, but it's created this instability. It's pushed electrons into the ring. You'll notice that here we have one of the 5 resonance patterns. This lone pair is allylic to the pi bond in the ring. An allylic lone pair was the very first resonance pattern you would have learned. And so that lone pair is really not existing just on that one carbon. Rather, it's spreading out over the whole molecule almost through resonance. So we have to show this resonance. It's really because of this resonance that this reaction can happen. This resonance helps to stabilize this intermediate. Another word for stable is lower the energy of this intermediate. And if the nucleophile doesn't have to create as energetic of a molecule, it can attack it more successfully more often. So the resonance is a really crucial thing. And you'll notice from this allylic lone pair, when you have an allylic lone pair, the lone pair goes to form a new pi bond toward the pi bond that it's allylic to. And the pi bond that it's going towards, that gets pushed, and the electrons form a lone pair on the atom, on the other end of the bond. So let me draw this new resonance structure. So now this has formed a pi bond here. The pi bond on the other end is still there. We have our bromine and our OH. And here we have the nitro group. Oops, and here this nitrogen should have a positive charge on it. Excuse me for that. And then the oxygen has a negative charge here. So make sure you put those formal charges there. Apologize for leaving that out so far on the nitrogen. And we also have this lone pair here now. This is a new lone pair that's formed. And the lone pair has a full negative charge. Well, this is now allylic to the other pi bond. So we can do a similar thing as before. The lone pair goes to form a new pi bond toward the pi bond that it's allylic to. And then the pi bond that has these incoming electrons, that breaks and forms a new lone pair away from the lone pair that's going towards it. And if you don't feel that confident with doing this allylic lone pair curved arrow pattern, let me know. I have videos from Organic Chemistry 1 that really practice this resonance pattern that might be able to help you out. So we'll draw this last resonance pattern in the ring here. So we've got this bromine, the OH. We have a new pi bond here. We have our nitrogen, oxygens, and now we have our lone pair here with the full negative charge. So now what ends up happening is the lone pair moves toward the nitro group. This is the part of the resonance structure that sort of illustrates why the nitro group helps this reaction to happen. This nitro group helps to pull electrons away from the ring, out of the ring, and that allows the incoming nucleophile to get there. So in this next resonance structure, you can really see the nitro group pulling those electrons out of the ring. So here, this is sort of allylic to that pi bond, so we can go to form a new pi bond. In this case, though, instead of forming a lone pair, this can form a pi bond here, and then one of the bonds on the nitrogen has to break. That's going to be the weakest bond, the pi bond between it and the oxygen, and that'll put a sort of negative charge on that oxygen. So now we have the nitro group sort of carrying the burden, helping to carry the burden of the negative charge. And so here we'll have these, we'll have this. That's a pi bond now, right? We had one, we're adding another bond there. And now both of the bonds to the oxygens will be single. Both of those oxygens will have a negative charge. So those are all of the resonance structures that happen, that try to help stabilize this intermediate to let this reaction happen. Finally, the leaving group gets expelled. So like with any substitution reaction, you have nucleophilic attack and loss of a leaving group. The loss of a leaving group happens, so here, in this last step. And remember, in terms of curved arrow patterns, loss of a leaving group subtracts. It takes things off of a molecule. So here, that's going to be the bromine. So this can go back here. This pi bond breaks, goes to form a new pi bond. And this pi bond moves over and kicks the leaving group off. The leaving group leaves. And you're left with an aromatic ring. So now you have all three bonds in the ring. You have your original nitro group, exactly how it was before. But instead of a bromine, you've replaced that or substituted it with your nucleophile. In this case, that was an OH. So, as far as curved arrow patterns go, the storytelling, it's just nucleophilic attack, loss of a leaving group, like any substitution reaction. The reason why this is a little more complicated is because of the resonance structures. And these resonance structures, this happens anytime a nucleophile attacks a benzene ring. And so you get these resonance structures very commonly. So this has a nickname, it's called a Meisenheimer complex. And it's really just drawing those resonance structures. That's the tricky part of this mechanism. But as far as the context for this mechanism goes, this is where you want a nucleophile to attack benzene. You don't want benzene to attack an electrophile like we focused on at the beginning of this chapter. Rather, you want a nucleophile to attack benzene. So you help to draw the electrons away from the benzene ring so it doesn't repel the nucleophile as much. And then you stabilize the intermediate through resonance. And that allows you to replace or substitute a leaving group with a nucleophile on an aromatic ring. So that's nucleophilic aromatic substitution. And the key thing is, because you have that nitro group on the para position, it's really pulling electrons out of the ring, so you only have to heat this up to around 70 degrees Celsius. If you want to do this reaction without having a para nitro group, then you have to heat it up much, much more. That's what we're going to see in the next video on the mechanism for elimination addition. Same type of reaction, substitution reaction, but there's no nitro group pulling electrons out of the ring. So to get this nucleophile to smack into this and not be repelled by the electrons in the ring, you really have to get it moving fast. You really have to heat the solution up. But we'll explore that in a separate video.